Okay, another quick lesson. This one's particularly important because it has its own name, and as I mentioned a number of times, if a theorem has its own name, you're going to get drilled on it quite a bit. Today we're going to talk about the mean value theorem. We've already done the mean value theorem. I'm sure you all remember, yes? Okay. What's the buzz phrase with the other mean value theorem? Trivia time. Well done. Slope from calculus equals slope from algebra. Okay. This is the mean value theorem for integrals, also known as the average value theorem. I got a joke for you first. Do you get it? Explain it to me.
Yes. It's because if you're doing it in terms of n, you had to put the n on.
There you go.
Is this going to be on the test?
Yes. Yes, I've actually gone to CVS and I've taken 314 pictures of different drugs and products from CVS, and I'm turning each one of them into an integral problem, which I will force you to solve on the quiz on Friday. So, good luck. You're going to love integrating hydrogen peroxide.
Friday?
Shouldn't be that hard. Go ahead and integrate this monster in terms of R. Now, the reason I included the joke was because it does illustrate one of the things we've talked about already. The dn, as Maria mentioned, the dn tells us that the variable for this problem is n. So that all of those other letters, A, S, P, I, R, I, are all constants. So when you take the integral of that constant, you get the constant times n. And then, of course, since it's an indefinite integral, you throw a plus c on the back end. Hence the reason we get bare aspirin plus c. Let's move on, shall we?
I get it. Oh my god, that's crazy.
Did that one take a while? Was it a joke grenade?
I didn't see the plus c part.
Okay. Let's just move on. We're going to start with something called the meltdown theorem, also a common phrase for the mean value theorem for integrals. You'll see why in a little bit. We're going to talk about MVT and how it applies to integrals. It's a pretty easy concept. And then you should be able to spell MVT. How was the aspirin? Aspirin was okay? Should I keep the aspirin? Lose the aspirin also? Lose the aspirin and the spell MVT? The aspirin good, but lose the spell MVT.
Yeah.
All right, I want it. I'll fix that for next period. Thanks for the input, guys. Appreciate that. You should also be able to read. I know, I'm asking a lot on a Wednesday. I can help you with the big words if you need. Okay, so here's the meltdown theorem as an example. I've got a glass full of crushed ice. Great question. Why crushed is relevant to the problem you'll understand in a minute. Cube, it wouldn't be as easy to understand it if it was cubed ice. So you've got some crushed ice in a glass. The top of that ice, as it says there, will be all uneven and scraggly. When the ice melts, you will get a horizontal, level glass of water. You're with me, right?
Sure. Yep.
That scraggly ice is going to have some very high points. You can see it in the picture where that piece of ice is sticking out of the glass. You'll have some very low points. When the water melts down, it will be somewhere in between. Okay? That level where the water is at is called an average value. So we're going to do the same thing with a function. We're going to melt down a function. So here's a function. Doesn't matter what it is, we'll call it f of x. And I have limits of integration, a and b. So if you think of a and b as the sides of the glass, the function then becomes the scraggly ice on the inside. When you melt down that function, two things happen. The stuff above melts down, the stuff below fills in. If you understand what's going on, let me ask you a simple question. if I've drawn my picture correctly, how do those two areas, the red area and the blue area, compare? They're the same, correct. So the area above the average value, okay, so there's the average value, that's the y value, that's the level of the water, will slice through that function. When it slices through the function, the area above the average value has to match the area below the average value, because it's an average value. Okay. So again, the A and B are the sides of the glass, the function is the scraggly ice. When it melts down, the level of the water is called the average value. Two different ways to use that. Sometimes you'll see it referred to as f of z, where z is the value, which I'll come back to in a second. Sometimes it'll be f of avg, f average. We'll use those two terms interchangeably. Question?
Why isn't Z in the middle of
I'm getting there. Hold on. Once we find, and I'm going to show you how to find that average value. Once you find your average value, you'll notice I'm missing one, but I just highlighted one of them. But there's actually 2 points where that average value hits the function. And if you follow those 2 points downward, they generate what's called a z term. It's the x value that when plugged into the function gives you the average value. Now here's a little more confusing things. That's a, bear with me. Okay. F of z, sometimes also referred to as f average. Sometimes they'll talk about the z term. However, other sources will also refer to it as a c term. I don't necessarily like that because it gets confused with the plus c. So I like to use the z term. Z is the x value, f of z is the y value. Just like you know that if you have x is the x value, f of x is the y value. You with me so far on concept? The concept, in my opinion, is more difficult than the application. The application is ridiculously easy.
Did you just draw a line to like?
No, I'm going to show you how to find that line.
Okay, so it's not like the exact middle of the function.
No.
Okay.
No. If I didn't tell you where f of z is, and you had to draw it, it gets a little tricky because you got to figure out where you're going to put that so that again the area above matches the area below. Okay. Like I said, there's the z. This function happens to have 2 z terms, but I just highlighted one. Okay, so again, are we okay on the concept? Yes? Or do you need clarification? Are we good? Excellent. Okay, finding that is very simple. All you're going to do is you're going to find the area under the curve, but you're going to multiply by that term 1 over b minus a. Okay, this is a more common way of phrasing it, but I prefer that. To find the y level of the water, you're going to find the area under the curve and multiply it by 1 over b minus a. How do I make that go away? Click this again. No. Okay, we good? Okay, here comes our example then. Again, another picture showing the same thing. If you understand what you're doing, then in the picture on the left, the light blue area there should match the red area above. And in the one to the right, the white area below matches the blue area that's not dashed above, using that same formula. Okay. All right, so here's our example. I saved you some hassles. I know that you can find the integral from 0 to 4 of x cubed, but that's not relevant to the problem. I would like to know what is the mean value theorem, or the average value on the interval from 0 to 4. Most of the time you're going to have to set this up from scratch, but I'll show you the setup here. First of all, where is it? There's the setup. This 64 came from up here. So what it would actually be, I should have included this. Okay. This is the same as that. Again, I didn't want to get bogged down in taking an integral. That's not what we're focusing on. When you're done writing, bust out your calculator or Desmos and do two things. Graph x cubed and then graph y equals 16. And take a look at that picture. Okay, so graph those two functions. Now notice we're going from 0 to 4, so your function is going to display a whole bunch of stuff beyond 4, because that's what it does when it graphs. If you just zero in on the area from 0 to 4, look at the area above 16. So it's bounded by y equals 16 and the function x cubed and the line x equals 4. You got a little triangle shaped thing there. And then look at the area below 16. That would be bounded by y equals 16, the function, and the y-axis, I think. See that right? Yeah. They may not look like it, but those two areas have to be the same. Because again, it's an average value. Now, you see where that line hits the function, yes? Where is that line? No, sorry, I asked the wrong question. Not where is the line. You know where the line is. Where is that point? That's the next step in solving the problem. I want to know what the x value of that point is. Now, with your calculator, you could find the point of intersection, get it that way. If you're on Desmos, you could probably find a point of intersection also, but we want to be able to calculate this mathematically. How do we go backwards? If I know the y value is 16, and I know the function is x cubed, how do I find the x value?
16 equals 18.
Bingo. 16 equals x cubed, which I have right there. So therefore, z is the cubic root of 16, which is 2.519. Now look at your graph. Does that seem about right? Does that point on your graph, the point of intersection between the line y equals 16 and x cubed, look to be about 2.5? It should be, because that's what the numbers tell us, and numbers never lie. Questions? Okay, there is a scenario that pops up every once in a while when you're solving an MVT problem that I thought I would warn you ahead of time. Let's suppose I'm doing a similar problem and I've got x squared, y equals x squared, and yada, 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 and I'm on an interval or whatever, and I figure out what my z term is, and when I solve this, I get x is equal to plus or minus some number. Let's say plus or minus 7, whatever. But I'm only on the interval from 0 to 5. No, not 0 to 5, 0 to 10. Even though the math tells us there's two answers, you're going to throw one of those out because it's got to be in the interval. If I go all the way back to this puppy, this guy, whoops. If you think of this as being a sine graph, which it is, this line y equals z is going to go on forever, and it's going to generate an infinite number of points of intersection. We're only concerned about the points of intersection that are inside the glass. Okay? So when you solve again for that z term, check to make sure that your answers, one of them, all of them, none of them, are inside your interval.